Hi everyone, Professor Rosenthal here, and today we're going to take a look at section 3.3, which is a technique to integrate complicated looking functions. We call this technique use substitution method to solve integrals. So today we're going to try, first of all, figure out which types of problems are eligible for this technique. So there are certain types of problems for which this technique works well. We're going to try to distinguish between problems that where use substitution is applicable versus problems where it's not applicable. And then we're going to try to integrate a variety of functions using the method of use substitution. So let's get started. And here's our first example, the integral of 5x plus 1 to the third power. Now, I'd like for you to think for a minute, if we didn't have this new technique, how would you go about integrating this? Well, there is no product rule for integration. So what you would have to do is you would have to expand this 5x plus 1 times 5x plus 1 times 5x plus 1 multiplied 3 times by itself. It's going to get pretty messy, right? And then you would have to integrate it term by term after you simplify that. But that's a lot of work. So for a complicated function like this, there's a better way. So we're going to use again the technique called use substitution. And the idea is we're going to try to write the entire integral in terms of a variable u, okay? And the goal is that this will be a simpler integral which will be able to solve much easier. So this would have been much easier if it was just of the form u to the third power, right? So I'm going to try to make this look like u to the third, okay? But along the way I have to deal with some additional constants to be able to go from this integral in terms of x to this integral, much simpler integral in terms of u. Well, for example, what is dx going to be replaced with? Can it be replaced with just du? Not so fast. Let's take a look. So if basically I'm calling my u to be replacing 5x plus 1. So think of it as du dx, the derivative with respect to x is 5, right? And if you multiply both sides by dx in a way, so du equals 5 dx. So you come over here, this middle part has been replaced with u to the third. But what are we going to do with dx? You come over here and say, okay, what is dx equal to in terms of a u variable? So we can divide both sides by 5, so dx is equal to du over 5. So I can replace dx with du over 5. So we were able to replace this entire integral with something much simpler of the form u to the third. You see this constant over here is not a big problem because we can always factor a constant outside of an integral sign. So this will be 1 over 5 times the integral of u to the third du. So now we went from an integral that had x's to an integral that has u's, but it's a much simpler integral to deal with. And along the way, what we had to do was decide what part of this integrand is going to be called u, and then over here temporarily we differentiated u so we can get dx written in terms of the u variable. So we differentiated u, and then from there we solve for dx, and we're able to come back, replace dx by du over 5. So now that we have a simple integral to deal with, let's go ahead and take the entire derivative. So integral of u to the third is u to the 4 over 4 plus c, and these two things up front are going to get multiplied. So we're going to have 1 over 20 times u to the 4 plus c. And let us not forget to put the u back in place. U was 5x plus 1. The original question had only x's in it. Our final answer has to be only x's in it. So we're going to do a backward substitution now. In other words, put u back in terms of x. Since u is 5x plus 1, just put it back in there to the fourth power plus c. So this is our answer. And the nice thing about integration is we can actually check to see if our answer is correct by differentiation, right? So let's check our answer here. So differentiate this answer, take the derivative of 1 over 20 times 5x plus 1 to the fourth power plus c. But derivative of c will be 0 anyway, so I'm not going to even bother writing it down. And let's see if that will give us the original expression that we started with. So to differentiate this, keep the constant as it is. bring the power down, keep everything inside the same, to 1 less power times the derivative of the inside, right? It's been a while since we did chain rule, so that's how we differentiate something like that. And then 4 times 5 is 20. It's going to cancel with the 1 over 20, and we're left with 5x plus 1 to the third. Indeed, that's what we had started with. So that tells us that this is indeed the correct antiderivative. No matter how weird this technique might have looked like, it did give us indeed the correct antiderivative. We know it's the correct one because we differentiated it and it gave us the original integrand. So we have a method of finding the integral of a complicated expression, and let's try to apply it for another question, and we're going to do several practice problems to see if we can really understand it. Okay, so let's take a look at the next one. Integral of x times 3x squared plus 4 to the power of 5 dx. This problem would have been a nightmare without u substitution. Think about it. You would have to multiply this quantity 5 times by itself, then distribute x one by one, then integrate by one by one. Again, very, very messy. Instead, let's see if we can do this with u substitution. With u substitution, you try to replace one of the complicated parts of this expression with something as simple as just u. Like, wouldn't it be nice if I could just have this appear as u to the 5 over here? Right? So with that, I would say, basically I'm saying, can I let u be 3x squared plus 4? Because if I can do that, then this whole thing becomes u to the 5. The problem will look a lot easier. But then the question is, what are you going to do with the x dx? Because that also has to be replaced and be written in terms of the u variable. So to replace x dx, we take what we call u to be equal to, and we differentiate both sides with respect to x. So du dx equals 6x. Multiply both sides by dx. Du equals 6x dx. Now in the last problem I'd solve for dx because that's all I had to replace. Other than this quantity here, there was only dx to replace in terms of the u variable. But here I have an x dx that I need to replace in terms of the u variable. So what I need to do in this equation is I need to solve for x dx. So let's solve for x dx, which will give me du over 6. So now I can replace x dx with du over 6. And again, if there's a constant, I can pull the constant outside. Now I have u to the 5 du left inside. So much easier to integrate this than to try to integrate the original quantity. So let's integrate it. U to the 6 over 6 plus c. And I can multiply these together, either put it up front or just write it as u to the 6 over 36 plus c. And then the next question is, can I leave it like this? We can't, right? Because the question was given in terms of the x variable. My final answer should be in terms of x as well. So u to the 6 would be, just put the u back in there, 3x squared plus 4 to the power of 6 all over 36 plus c. And of course you can also write it like this if you prefer, 1 over 36 times 3x squared plus 4 to the power of 6 plus c. And again, you can certainly differentiate this to show that the derivative of that will give you the same quantity that we started with, and that would be a way to prove that this is indeed the correct antiderivative. Okay, in the beginning these questions might look a little bit weird, and it takes a little bit of time. I would say like by the time you get to the third, fourth, fifth example, I think it makes a lot more sense because the method is quite repetitive. But in the beginning it's perfectly fine if you're a little bit confused, where is all the stuff coming from. So I would highly recommend pause the video frequently, go back and see if you can do the problem from the beginning to the end after you've seen the solution.